Hi, welcome to me313 Mechanical Engineering Thermodynamics. The topic of this video is Stirling and Ericsson cycles, and the section in the textbook if Signal and Bowles is section 9.7. Alright, here are the learning outcomes for this video. At the end, you should understand how Stirling and Ericsson cycles operate. You should be able to recognize how these cycles are reversible. You should be able to solve for the thermal efficiency of the Ericsson cycle. And you should understand some of the engineering difficulties in designing practical Stirling and Ericsson engines. Alright, so first I want to discuss a little bit about reversibility. Remember, there's reversibility. We talk about things that are internally reversible and externally reversible. We talked about the ideal Otto and diesel cycle, and we said that they were internally reversible. And what that meant was inside the system, there was nothing such as friction or heat transfer across finite temperature gradients. But the thing is that they're not completely reversible because they're not externally reversible. And so let's kind of look at those cycles for a little bit and recognize why that is. From the left over here, this is the Otto cycle that I have. This is a PV diagram. And for example, going from step 1 to 2 was an isentropic compression step. That would be reversible if there was no friction going on, and during that compression there's no heat transfer. So that's actually a completely reversible step. However, 2 to 3, that was during the spark ignition. And then what was happening is the volume didn't change, the pressure increased. And that means that the temperature also increased as we move through here. So point 2 going to point 3, we were at some moderate temperature up to a very high temperature. Now, in order for that heat transfer to happen, what we had was burning fuel that was at some temperature, TH, that was actually greater than the temperature all along those points. And at each point, energy went from that TH down to here to raise the temperature to that point, to that point, to that point. And as the temperature increased going 2 to 3, but every time there was energy coming from some high temperature source, which was the initially burned fuel that was then heating the rest of the air. And so since there was heat transfer occurring across the finite temperature gradient, this cycle is not externally reversible. We can say the same thing over here when we had the heat loss. This right over here is Q going out. And this was going into CL, some lower temperature, and as it went from 4 down to 0.1, there was heat transfer across the finite temperature gradient. Okay. You see a similar thing in the diesel cycle. Again, going 1 to 2 is isentropic, and that's okay. That can be completely reversible, both internally and externally. However, 2 to 3, this is again where this is our energy going in, which was the burning fuel, and the temperature is increasing as I go from 0.2 to 0.3. And so at each point there's going to be some TH value that is greater than the temperature all along there. So there is, again, heat transfer across the finite temperature gradient, and that makes that not externally reversible. And the same argument that I made over here for going to 4 to 1 for the Otto cycle is true for the diesel cycle. So therefore we say that they're internally reversible. There's no friction. Again, this is the ideal cycle, but they're not completely reversible. So entropy is generated in the universe even with an ideal cycle operating. Now there are a couple cycles though that are completely reversible, both internally and externally. One we saw before, which is the Carnot cycle, which has these 4 steps where we have 2 isentropic steps. This is showed the Carnot cycle on a TS diagram. We have 2 isentropic steps and then 2 isothermal steps. And so we have energy coming from some value TH, we have energy going to some value TL, but it's occurring in keeping the temperature constant. And so in theory, there could be no temperature gradient. Now we recognize from a practical point of view, heat transfer would be very slow if this was just TH and the fluid was at TH, and there's going to be some teeny bit temperature difference, but essentially it would be completely reversible. Here we show the Carnot cycle on a PV diagram in the ideal gas space. Well, one of the things to recognize is it's very impractical to build Carnot cycles. It's very, very difficult to go ahead and have steps that are completely isentropic and then having heat transfer where the temperature is constant. But there's a couple cycles that come pretty close that generate no entropy that are both internally and externally reversible. And one of those I'll talk about here first is the Stirling cycle. So this cycle over here is the Stirling cycle. All right, and so I have it shown as a TS diagram and a PV diagram. So let's look at the TS diagram first. We see this 1 to 2 where we have heat transfer, energy going in at a constant temperature. It's very similar to 1 and to 2. And then we have the energy going out. This is Q out, again at a constant temperature TL, which is very similar to the Carnot cycle. But a couple things that are different. We're going to see why that is here in a minute. But instead of there being isentropic steps, we have isochoric steps, or where the volume is constant, instead of the entropy being constant. And so what that does, and we'll see why that has to happen in a minute, if I wanted to go ahead and reduce the temperature, so let's imagine an ideal gas at this point, I want to go ahead and reduce the temperature, and at the same time, I'm going to go ahead and keep the volume constant. Well, the only way I could do that, like this is just like a box with the temperature going down, is if heat left the system. And it's cooling down, and so if it was to be losing heat, it couldn't lose it to some sink that would be at TL, that would be like the Otto cycle or diesel cycle, where we'd have temperature across the finite temperature difference. So it uses this thing called a regenerator, where this is the energy, stays within the system, and it gets dumped over to a fluid that's on the opposite side. And we'll see how we do that in practice. And that way, since there's always heat transfer across an infinitely small temperature gradient, that is also isentropic. Here I show the same cycle for the Stirling cycle on a PV diagram, and here's the important step, which is the regenerator, where as the temperature drops from 0.2 to 3, it's actually heating the fluid as it goes up here from 4 to 1. And so because, again, there's no temperature, no heat transfer across finite temperature gradients, this is a completely reversible cycle. This is the Stirling cycle. So let's go ahead and look at how this works in practice a little bit more. So again, this is the Stirling cycle. This is the TS diagram at the top, PV diagram on the bottom. And so let's look at these steps from a practical point of view. So we're going to go from point 1 to 2. And so this state I show up here is point 1. And so here's a Stirling engine. We've got a cylinder with 2 pistons. And then there's this material in the middle. And this is what's called the regenerator material. Think of this as maybe like a porous metal. So it's something that's rigid, but fluid can move through it. It's like a big sponge, a big metal sponge. Now what happens is I go from 1 to 2, the temperature remains constant, the entropy increases, and that happens by heat going in. And what happens, in order to keep the temperature constant, this piston has to slowly move out so that it doesn't heat up. So as I add energy, it moves out, and we're able to go ahead and move from point 1 to 2. All right. Then I'm going to go, so now I'm over here at point 2, and I want to go from point 2 to 3, and I'm going to keep the volume constant. So I'm keeping the volume of this fluid right here constant. But what I'm doing is I'm dropping the temperature. I'm going from a TH to a TL. And so these 2 pistons, right, are now going to go ahead and move from here all to the right, keeping the volume of this material constant. And what ends up happening is the temperature drops to TL. And the way that it does it is that this material has a very high heat capacity, and so as it moves through, this left-hand side is going to be at a TH, the next one is going to be somewhere in between TL, and it goes ahead and keeps this temperature gradient in there. So it has a high heat capacity, low thermal conductivity, and so now this material is at TL. And so what's happened is it just dumped heat into the fluid dumped heat into this material. That's the regeneration step right there. Now, so we're at point 3. If we wanted to go from point 3 to point 4, we want to go ahead and keep the temperature constant as I move across, and I'm going to go ahead and remove heat out. And so in order to do that, to keep TL constant, I go ahead and compress this piston up here while keeping this one against the regenerator. And then if I'm going to go back from 4 to 1, so this is the same point over here, I'm going to go back up from 4 to 1. Again, I move the material across, pushing it here. Remember, here's the regenerator, and it's got the left-hand side is warm, the right-hand side is cold. As this fluid moves through this porous material, it's going to go ahead and heat back up to TH. And so there's that regeneration step on the receiving side. That's the way the Stirling cycle does, and this regenerator is a key component to go ahead and kind of just stores this energy temporarily. It stores it as it comes out over there, and then it's received over on the left-hand side. Here's a diagram of kind of a Stirling engine that's operating, okay? And so right over here, this is kind of the left-hand side of the diagram I had before. This is what we showed on the left-hand side. This one over here is the right-hand side. Right? So this is at TH. This is the hot temperature. This right over here is at TL. And you see the pistons moving back and forth. And then this material right in here is all the regenerator. And so the fluid's kind of going back and forth through the regenerator. And the regenerator is just a storage of energy such that we can go ahead and keep this thing completely reversible, and we're just interacting with 2 temperature sources, one at pH and TL. There are a few practical Stirling engines. They're still kind of in the research stage, but they do exist. Here's one that's in Spain, and this is the Stirling engine right up here, and this is just a big concentrating mirror that's go ahead and reflecting a bunch of sunlight onto the hot side of the Stirling engine. And the reason people use Stirling engines for these types of generators is that concentrated solar energy, although that would be pretty hot, is still what's considered a pretty low quality heat. And so in order to make these practical, you need to essentially be pushing up against the Carnot limit in terms of efficiency. So a lot of the research is done using Carnot engines to go ahead and, I'm sorry, not Carnot engines, Stirling engines to go ahead and convert this type of energy. This is obviously a very desirable, this is a completely renewable source of energy, sunlight, and then we're operating at the upper limits of what kind of engineering efficiencies that we can have. So that's a reciprocating cycle. It's completely reversible. There's a continuous cycle that's also completely reversible. That's called the Ericsson cycle. On the left-hand side here, I show the TS diagram and the PV diagram. What's interesting is the TS diagram is almost exactly the same as the Stirling cycle, except now instead of the volume being constant, we have pressure constant across these two lines right over here. But again, we're using a regenerator. And so let's go ahead and look at it. There's a diagram here of where the Ericsson cycle is. And so if we start over here at point 1, when we're at a high temperature, and then we're going to go ahead and increase the entropy. So point 1 would be right there. That's entering the turbine of the system. Energy is going in, so Q in is going there. This is Q in, going in right there. And since this is expanding while the temperature is constant, remember in terms of entropy, for an ideal gas, if it expands, the entropy increases because there's more uncertainty of where it is. So 1 to 2 is an increase in entropy while the temperature is held constant. So we have to add heat right at a constant rate such that as this expands, we're always keeping the temperature constant and the entropy increases. And so then there would be the exit of the turbine, which would be at point 2, which is right there. So now this is going to be a constant pressure going to point 3. Point 3 is going to be the other side. The regenerator, heat leaves this. And again, remember, this is the hot side. So this is going to be over here at TH. And then eventually it's going to come out at TL. And so there's this temperature gradient through here. And this is just a countercurrent heat exchanger. Fluid's moving in this direction, dumping heat to fluid that's coming in the opposite direction. So fluid coming out of here is also going to be a TH. This is going to be like TH minus 1 right there. This will be at TH minus 1 as well, all the way down to TL as I move through. So then I'm at point 3. And this was a constant pressure cycle. So going 2 to 3 was a constant pressure cycle right down there. And now I'm going to go into the compressor, going from 3 to 4. And we're going to go ahead and compress the material at a low temperature. Now as I compress it, I'm putting energy into it. Right? It's coming from the shaft work. It's coming off of here. And so if I don't want it to heat up, I want to remain the temperature constant, I'm going to have to remove some heat. So there's my Q out step right there, or 3 to 4 Q out going there. And I do have to do it. It's difficult to engineer because I've got to have it designed such that as I compress it, each time it goes through a particular stage of the compressor, I remove just enough heat to keep TL constant. Then I'm going to go through the countercurrent heat exchanger. There's the regenerator just dumping heat through into this fluid to come out at TH. There's an Ericsson cycle. It's only interacting with 2 temperature reservoirs, one at TH, one at TL. If it's internally reversible, meaning no friction, therefore it would be completely reversible and would have the same efficiency as the Carnot cycle. Right. So let's go ahead and do an example. We're going to solve for the efficiency of the Ericsson cycle. So here I've got a picture of the Ericsson cycle again here up on the right, just to remind you. We're going to be using helium as the operating fluid. And here's the engine, and it's operating between a low pressure of 100 kPa, high pressure of 2 megapascals, low temperature of 40 degrees Celsius, and a high temperature of 900 degrees Celsius. All right, and so what we want to do is we want to go ahead and calculate what the thermal efficiency of that is. So what we're going to need to do is we're going to need to determine some of these steps. And so let me go ahead and write my steps points here. 1 to 2, 3 to 4. And in fact, you can go ahead and I'll go ahead and draw my TS diagram. It'll help us remember what it looked like in the Ericsson cycle. So this would over here be point 1, 2, 3, and 4. And if we kind of look at the PV cycle. Over here we have 1 to 2, 3 to 4. 1, 2, 3 to 4. So, all right. Well, if we look at, for example, let's just start off looking at the compressor stage, going from 3 to 4. So this is 3 to 4, but we're going to go ahead and compress it. So going in this direction. And so there's some work that's coming in. It's coming in off the turbine to go ahead and compress this material at a constant temperature TL. And we said that this is internally reversible, meaning no friction. So if I want to know how much work is actually going in there, I can go ahead and find the work of the compressor. If you remember what the work of a compressor that's reversible, the equation, if the temperature is constant, it ends up being R times TL times the natural log of pH over PL. So go back to chapter 7 and review that if you don't remember where that equation came from. What we did is we integrated, just to remind you, we integrated V dP for an ideal gas to end up with that right there. So let's go ahead and solve what the work of that compressor is. We'll put some numbers in there. We have helium, so the value of R is 2.077. The temperature TL, we're at 40 degrees Celsius, which would be 313 Kelvin. You need to do all this in absolute. And now the natural log of the high pressure over the low pressure, so 2,000 over 100. And if we go ahead and put the numbers in there, that comes out to 1947.5. And that's going to go ahead and be in terms of kilojoules per kilogram. And one of the things to note is that, right, so there's my work going into the compressor. This is Q out, coming right there. And the temperature is constant and I have an ideal gas. So you think in terms of your energy balance, right? We've got the change in internal energy. Well, that's going to end up being whatever heat I put in minus the work that comes out. I realize Q is equal to W for that. So this is also equal to Q out. The amount of compressor work I put in is the amount of heat that comes out. If there's no temperature change, delta U is going to end up being 0 for this, right? So now we realize that the compressor work that goes in here is the exact same that's coming as Q out. Now if we look at the turbine, so go ahead and there's Q in, and then it's going to go ahead and be generating some work. We have the exact same arguments that we just did. Now we're just operating at TH. So the work of the turbine is going to be simply RTH, natural log of P high over P low. Similar equation we had over here, except now TH is at 900 degrees Celsius. And so if I put in that number, what I get is a different value, which is 7298.5, and that's in kilojoules per kilogram. So that's the work of the turbine. And again, with a similar argument, I realize that that right there is equal to Q out, the amount of heat that leaves the system. All right, so now I have Q in and Q out. I have the net work, which is the difference between the work of the turbine and the work of the compressor. So we can go ahead and calculate what our efficiency is. So our efficiency, which is the net work over the heat that goes in, and in fact, I'm just going to go ahead and rewrite it this way, 1 over Q out minus Q in, because we had those numbers directly, and let's plug those in there. Q out, right, which was that was what the compressor work is, so that was 1947.5 kilojoules per kilogram, and that was over what was Q in, which was the work of the turbine, and that right there was 7298.5 kilojoules per kilogram, and that right over there becomes 0.733 or 73.3% efficient. Now, one of the things to remember, we just said that an Ericsson cycle operates just like a Carnot cycle. It has the same efficiency of a Carnot cycle. So we could have actually just went ahead and solved for what the Carnot efficiency is, which you remember is 1 over TL over TH. And so if I put those numbers in there, 1 over TL, TH, it's 1 over 313. That's my 40 degrees Celsius. T hot is 1173. That's TH. That number right there, not coincidentally, is 0.733 or 73.3% efficient. So in fact, I didn't have to actually do all those compressor work equations if I recognized an Ericsson cycle is a Carnot cycle, has the same efficiency, All I had to know was TH and TL. But I think it's also interesting to see that you can analyze this just like a normal cycle, and you end up getting the exact same answer either way.